Welcome back friends. We are going to continue our discussion on the three-phase AC system. So today in this lecture we are going to discuss the AC power generation. So we shall start with the single phase AC power system and then we shall complete our lecture with how the three-phase AC power can be generated. Because in last lecture, as I already told you, that in general worldwide the power generated is three-phase in nature. Power transmitted and distributed is also three-phase in nature. And finally we are getting the power at our home, that is single phase, from the three-phase system. Or say in some application, if we require some other number of phases power, like melting application 48 phase power is required, then it is also possible that it can be obtained using the three-phase AC system or three-phase AC power. Okay, so now the AC power generation. Now three-phase generation, that is our final objective to understand what is the three-phase generation. So now you will learn the Faraday's law, and as per the Faraday's law, three things must be present in order to produce the electrical current. Very important. Three things must be present in order to produce the electrical current. The first thing, that is known as the magnetic field. Second thing, that is known as the conductor. And third thing, that is relative motion. Relative motion between the magnetic field and conductor. If magnetic field is there, conductor is there, but there is no relative motion, that means current cannot flow through the conductor. You already know that the Faraday's law of electromagnetic induction is E is equal to minus n into d phi by dt, where the n is number of turns. E, that is the EMF induced. If the EMF induced in a coil and coil is closed, that means either connected with load or shorted at its end, then due to this some current will pass through the coil. But E is equal to minus n into d phi by dt, so there must be some rate of change of flux. So the rate of change of flux is essential. If there is no rate of change of flux, that means there is no induced EMF. Because if there is no rate of change of flux, d phi by dt will be equal to the 0, and hence E is equal to 0. So as in this slide, three different things, that are the magnetic field, conductor and the relative motion, that is the essential thing as per the Faraday's law. And we are getting the three-phase AC power using the Faraday's law. Now the conductor cuts the line of magnetic flux. A voltage is induced in the conductor. Now here again the question may be, okay, the relative motion should be there between conductor and magnetic field. Then should conductor be stationary or magnetic field be stationary? This is a question. Relative motion, that means either conductor is moving or the magnetic field is varying. Both these are the different case. Finally, at the end of the lecture, I will ask few sentences about both these things. But if conductor cuts the line of magnetic flux, a voltage is induced in the conductor according to Faraday's law. The law is also known as the Faraday's law of electromagnetic induction. Okay, so voltage will be induced in the conductor, and due to which you can say that the current will pass through the conductor. Now here the voltage induced in the conductor is not constant. Voltage induced in the conductor is varying with time. The voltage induced in conductor is varying with time, and it may have the positive value as well as negative value. That means the voltage induced is, right now we are considering that is the AC, because the alternating in nature. Okay, now the voltage induced depends on the direction and speed. Direction and speed at which your conductor cuts the line of magnetic flux. Obviously, in this case, we are going to consider the case in which the magnetic field we are considering the stationary or say constant, and our conductor is moving. So, the direction and speed at which conductor is moving will also affect the voltage induced in the conductor, and hence finally the current passing through the conductor. So that is the thing that we are going to discuss now. You try to concentrate some terminology, that is, you can say that in previous chapters of electromagnetism you have already studied this thing, but we are trying to repeat several things here also. Now here the magnetic field, conductor and relative motion. So how we are relating these three individual terminology that we are going to discuss. Now we start our discussion with the generating a single phase supply AC or single phase AC voltage. So now here this is very important thing. See, in this case we are having the magnet which is stationary. This is the north pole of the magnet, this is the south pole of the magnet. Okay, here we are adopting several terminology and we shall follow this terminology only. This is north pole of the magnet, this is south pole of the magnet. Now this is the line of flux. Always, obviously you already know that it is from the north to south. That means the flux is from the north to south. So all these are the line of fluxes. The arrow indicates the direction, that is from the north toward the south. And this is the conductor. So this is the initial position of the conductor, or we are considering this as the reference position of the conductor. Okay. Now the conductor is moving in say clockwise direction. So the arrow shown, this end of the conductor will move up, this will go down. Suppose here it is rigidly fitted, then it is moving in clockwise direction and it may follow the circular path. These are the things that we have to remember. Again I would like to repeat, this is your magnet having the north pole and south pole. The line of fluxes are from north pole to south pole. The arrow shown on the flux line is saying that it is from north to south. This is the conductor which is say right now in a horizontal position. You can say that it is perpendicular to the line of flux. We can say that it is perpendicular to the line of flux. The conductor is moving in this magnetic field in clockwise direction. When we shall start the movement, at that time this arrow, that means this end will go up, and at the same time this end will go down, and conductor will follow the circulating trajectory, or it will be its movement path. That is the thing. Okay. Now here if we are saying that the motion is parallel to the flux, this is the direction of motion of the conductor. See, this is the direction of motion of the flux. So the motion of the conductor is parallel to the flux. If it is parallel to the flux, that means no voltage will be induced, because you can say that there is no relative movement. If motion is parallel, then there is no relative movement, and hence you can say that the no voltage is induced. So again, to have the voltage across the conductor, we require three things. The first thing, that is this magnet, north and south, it is present. Second thing, that is the conductor, it is again present. And third thing, that is the relative motion. But as in this position of the conductor, motion is parallel to the flux, there is no relative motion, and hence the no voltage is induced. Okay. So now if we try to draw the waveform with reference to time, say the x-axis is my time and y-axis is my voltage, then in this position, due to motion in parallel to the flux lines, no voltage is induced and hence there is no voltage induced, so the voltage induced is equal to 0. So this is 0 line. Okay. See, we are trying to understand the AC power generation. Okay. We are starting from the single phase and we shall complete our discussion with, you can say that, the three-phase AC power generation. Okay. So now this nomenclature, terminology, and as line of flux, its direction and the motion direction. All this we shall follow in our successive slides. Okay. Definitely I will repeat as and when required. So you can say that when the conductor is horizontal, or you can say that it is perpendicular to the line of flux, the motion of conductor is in parallel with the flux, hence there is no relative motion, hence no EMF will get induced and hence 0 EMF is induced. That is the thing. Now consider the second case. Now the conductor, as discussed in the previous slide, is moving in the clockwise direction. Okay, conductor is discussed in the previous slide, moving in the clockwise direction. Against now there is no change in the magnet and magnetic field. That means here in this case our magnets are stationary. Magnets are not moving, conductor is moving. Conductor is moving clockwise. Magnets are not moving, they are fixed, so the line of flux are also fixed and it is from the north to the south as shown in the figure. Now here you can observe the two different things. Here the cross is there at this end of conductor and here the dot is there at this end of conductor. Now what is the meaning of the cross and dot? That I would like to tell you. In this case, suppose if I am drawing the arrow, I am sitting over here. So from this, if I am observing the arrow, then I am observing that it is looking like a dot. But suppose if I am sitting at this point and arrow is like this, then I am observing the arrow as cross. So if my direction of current I am considering as the arrow, if my direction of the current is inward, at that time I am saying that it is cross. That is the inward direction of the current. Inward direction of current. And if my direction of current is outward, direction of current, then I am observing the dot. So the dot, that means the current is coming out. Cross, that means current is going in. These are the current direction. So this you have to remember. This nomenclature you have to remember and we have to follow this nomenclature. So now as shown in the slide, here the cross is there. Cross is there, that means from this the current is going inward the conductor and from this end the current is coming out of conductor. See, if I am saying that the current coming in or out, that means there is closed path. If there is no closed path, then there is no question to flow a current. As you can see that here the EMF is not induced, that's why no flow of current, that's why there is no cross, no dot. Got it? Okay. As there is no EMF, no current, even though the path is closed, EMF is 0, current is equal to 0. But in this case you can say that now the EMF will be induced. Why EMF will be induced? Because the conductor is moving with some relative motion. As the conductor is present, magnetic field is present, and relative motion is there, some EMF will be induced. EMF will be induced in the conductor, and the conductor is a coil which is closed path, say. Then the current is passing through the coil, and that current, here we are saying that current is going in at this end and say coming out from this end. This you have to remember. Now here one more thing that you have to remember is there, if the current is coming out and your conductor is moving toward N, then the positive EMF is going to rise or is going to increase. That I am going to explain you later on also. Only the thing is, in this case in horizontal position, when the conductor was perpendicular to the line of flux, at that time EMF induced was 0. But now the conductor is moving toward the north pole due to the clockwise movement, and if the end of conductor which is moving toward the north pole, at that end if current is coming out, then the voltage is rising or the EMF induced is going to rise. So that you can see here. Here in this case, say this is the 45-degree position of the conductor. So we are considering the motion of the conductor when it is placed at the 45 degree to the line of fluxes. Now if it is at the 45 degree, then you already know that due to the sinusoidal distribution we are getting the induced voltage which is equal to 0.707 of the maximum. That is maximum voltage, you can say that the peak value of the voltage. And if we are saying that the maximum voltage or say the peak value of the voltage is 1, then we are saying that we are reaching to the 70.7% of the maximum voltage, and our graph of the voltage will be like this. Here you can say that this value of the voltage is 0.707, and this is the phase, that is equal to 45 degree. So if the conductor is in this position, that is equal to 45 degree, that is this position, that is equal to the 45 degree, then the voltage induced in the conductor is equal to 0.707 of maximum. Assuming maximum is equal to 1, then this voltage will be equal to the 0.707 volt. So this is the thing. Okay. Again, the conductor is in motion, it is continually rotating, and this is the voltage in the conductor at an instant when it makes angle is equal to 45 degree with the line of flux. Okay. Now here you can say that in between also there is induced EMF 45 degree 70.7. Suppose if I am trying to obtain the EMF at say the 30 degree, then at 30 degree it would be equal to the sin 30 is equal to 0.5. At 0 degree it is equal to sin 0 is equal to 0. Basically it is following the sine form. Okay, that we shall discuss later on also. Okay, so at 45 degree 0.707, that is the EMF induced. So now again after 45 degree, if I am drawing the waveform, so now my conductor is in parallel to the line of flux. Okay, but here you see, you observe the dot point is toward the north pole. See, the position of north and south pole is not changed. the line of fluxes are also not changed. Only the change is there in position of the conductor. So now if my position of the conductor is like this, that means it is parallel to the flux. But the motion of the conductor is now perpendicular to the flux. Remember, the position of the flux and motion of the conductor, position of the conductor and motion of the conductor, both are different things. Here you can say that as the motion of the conductor is perpendicular to the flux, you can say that it will observe the maximum flux change. So here the d phi by dt may be maximum. Okay, but so what happens? The motion is perpendicular to the flux and hence the induced voltage is maximum. So now again, as you already know that the motion is perpendicular, so we can consider the angle is equal to 90 degree. In previous case, we considered that the angle was equal to 45 degree, and that's why the induced EMF was equal to 0.707 times that of the maximum. But here you are having the motion which is perpendicular to the line of fluxes. You can say that the induced EMF is maximum, and as it is as per our expectation, if we draw again the graph, then here at 90 degree perpendicular, that is the 90 degree, at 90 degree we are getting the maximum amount of induced EMF. Okay, so now here we can say that if this is 1, then in previous case at 45 degree it was 0.707. Again here we can observe the direction of the current through the conductor. Here you can say that if the line of fluxes are from the north to south, obviously it will be always there. The line of fluxes are from north to south. Here the current passing through the conductor is coming out toward the north pole, and when in this condition current is coming out, the induced EMF will be maximum, or it will have the maximum value. You can say that it will have the peak value, or you can say that this is the amplitude of the induced EMF. Okay, so till now we have considered the three different cases. In first cases, our conductor was perpendicular to the line of flux. In that case, you can say that the line of flux and the conductor both are at 90 degree, but the motion of conductor and line of flux both are in parallel. As the motion of conductor and line of flux both are in parallel, there is, you can say that, no relative motion, and as there is no relative motion, we can say that there was no induced EMF in the conductor, and hence no current was passing through the conductor. That was the first case that we have considered. In second case, the conductor was moving at some speed and it was at 45 degree to the line of flux. So now again here we are saying that as it is moving, it cuts the flux. That means due to motion, it cuts the flux and EMF is induced in it. EMF is induced in it is 70.7% of the maximum EMF. 70.7% of the maximum EMF, because you already know that that is the relationship of the sine term, that is equal to sine 45 degree. That is the thing. In third case, the conductor was moving and at some instant of time it is in parallel with the flux. Conductor, the position of the conductor is in parallel with the flux, but the motion of conductor is now perpendicular to the flux. As the motion is perpendicular to the flux, we can say that it will cut the flux at highest rate, or you can say that the d phi by dt will be maximum. If the d phi by dt is maximum, that means the maximum amount of EMF will get induced, and if the maximum amount of EMF will get induced, then you can say that okay, now that is the peak value of the induced EMF in the conductor, and it was the position of the conductor at an angle which is equal to 90 degree. So now we are going to further check the induced EMF in a conductor with different movement of the conductor. Again, there is no change in the position of the north and south pole, because here in this case we are assuming that the magnetic field is stationary and conductor is moving. Remember, I would like to say again that it is possible that the magnetic field may be revolving and conductor is fixed. But right now we are getting the magnetic field is stationary and conductor is moving. Okay, again I repeat that the essential condition for the EMF induced in the conductor according to Faraday's law of electromagnetic induction is the magnetic field is required, which is set up by the north and south pole. Second thing, presence of conductor is required, and third one is there must be relative motion between the conductor and the magnetic field. So we are going to consider the next case. In this case you can say that again the conductor is placed at the 45 degree, but now there is difference. In first case and in earlier case of the 45 degree and in this case of the 45 degree. Now the difference is that in earlier case of the 45 degree, considering the direction of the conductor, it was moving toward the N pole. In earlier case of the 45 degree, you can say that the conductor was moving toward the N pole. Say this is the conductor, it is at the 45 degree, but it is moving toward the N pole. As it is moving toward the N pole, its EMF is going to rise, and it is 0.707 of the maximum value. But in this case, in this 45 degree, here the conductor is moving away from the north pole. Here it is moving away from the north pole, but as it is at the position of the 45 degree, you can say that here the EMF induced is equal to 70.7%, same as in the last case. But now it is going to decrease from its previous value, peak value, and it will reach to the 70.7%. See again, at this point and at this point, that means at 45 degree and at 135 degree, in both the case, the EMF induced in the conductor is 70.7% of the maximum value. But at 45 degree it is raising, and at 135 degree it is decreasing, or you can say that the waveform is declining. So now at 135 degree, here you can say that it is the thing like that. Okay, again the direction of motion is same. Say it is clockwise direction. There is no change in the magnetic field. Here the magnetic field is assumed to be a stationary. The conductor is in magnetic field. It is interacting with the magnetic flux, and say it is moving in clockwise direction. So, okay, so we are going to consider the next case. Again in this case, you can say that now your conductor is horizontal, that is, it is say now the 180 degree. If it is 180 degree, again, even though conductor is parallel to the flux, its motion, conductor is perpendicular to the flux, its motion is parallel to the flux line. As the motion of the conductor is parallel to the flux line, it is as good as it does not conduct, it does not cut any fluxes, and hence you can say that here no EMF will be induced. So again the EMF induced will become equal to the 0. Okay, so now if you see that at 0 degree, what was there? Here was the green and here is the yellow line, yellow end. Now at 180 degree, the green end is here and the yellow end is here. Okay, so in 0 degree onward, the conductor with outgoing current was moving toward N. Here now it is going to moving toward S. That is the difference. Very important difference, because this is the difference which will describe the positive half cycle and negative half cycle of the AC system. Okay, if you understood this difference, then it is okay. So now assume that again now the conductor is moving 45 degree in this position. Will there be a dot or cross? At this end, will there be a dot or cross? Because as you can see that in earlier case, here the dot was there, here the dot was there. Okay, now here you can say that there is no flow of current, so there is no question of dot or cross. But for next, what will be the position? So let us see what is the position. Now see what happened. Here now this end which was dot till this point will become cross. What it means? Earlier in previous half cycle, the current was coming out through this end. Now is going in at this end, and current which was coming say the into this end will be out of this end. Now in this case what happened? The current is coming out dotted. In previous case here it was cross. Okay, now in this case here it is dot. So what is the difference? The difference is because now the conductor changes its position. In earlier case this end was moving toward the N pole, and in this case the same end is moving toward the S pole. Okay, so the end which is moving toward the N pole will give you the positive voltage, but now this was the negative end and it is now moving toward the N pole. So you can say that here the current direction is changed. In this end the current was coming out, in previous case is now going in, and at this end the current which is going in previous case is now coming out. So that is the direction in current is changed. If the direction is current is changed, then as it is 45 degree, again the induced EMF is 0.707, and you can say that you are having, due to the change in the direction, here you can say that this is the negative value of the voltage. So what I mean to say is, here the end of the current, end of the conductor which was previously moving toward the north pole is now moving toward the south pole. So earlier the voltage available was plus 70.7% of the maximum at 45 degree. Now here the voltage available is minus 70.7% of the 45 degree. If I am considering this as 45, so it is 180 plus 45, it is equal to 225 degree electrically. Okay, so now here again this is the case when conductor is in parallel with the line of flux, so it is in line with the flux, but you can say that the motion of the conductor is now, you can say that perpendicular to the line of flux, and hence it cuts the flux maximum. Okay, so now see what happened here. Here as this end is reached to the south pole, as this end is reached to the south pole, here you can say that you will have the negative maximum voltage, which is as per the expectation. So the induced voltage is maximum, and you can say that now we are reaching to this point, this is 90 degree. In fact, you can say that it is 180 plus 90 is equal to 270 degree electrical. Remember, here whatever the degree that we are trying to draw on the x-axis, that is, say now the 180 plus 90 is equal to 270 degree. And finally again, suppose it is at 45 degree. Okay, but now this end is moving away from the south pole. Away from the south pole, that means the negative voltage is going to reduce. Okay, at this point the negative voltage is maximum. At this point negative voltage was 0.707. At this point it was 0. So 0 to minus 0.707 to minus 1 to minus 0.707. So now you can say that it is again minus 0.707. So that is the thing that we have to remember. And now there will be the point at when the conductor will again be in a horizontal position, or it is more precisely we can say that it is perpendicular to the line of flux. So now see, in this case, now the conductor is again in this position. That means conductor has complete its one rotation of 360 degree electrical. And here you can say that again, as it is in the horizontal position, it is perpendicular to the flux, but the motion of conductor is now parallel to the flux. If it is parallel, that means there is no cut of the flux. Flux is not cut by the conductor. And as flux does not cut by the conductor, you can say that no voltage is induced, or the induced voltage is 0. So we are talking about this position. So this position is now your 360 degree position, where the conductor has completed one complete revolution from 0 degree to 360 degree. Again, if we are going further, then again at 45 degree we shall have the 0.707 positive voltage. Okay, so these are the things. I would like to repeat several things again for your reminder that in this case we considered the magnetic field, that is constant or stationary. Magnetic field is not changing, it is constant magnetic field. The constant magnetic field is obtained using the north and south pole. Okay, line of fluxes are drawn from north to the south pole. It is fixed. Conductor is moving. Conductor is moving in clockwise direction with some constant velocity, and depending upon the position of the conductor, you can say that this is the thing that we have to observe. Now, in case of the three-phase system, we are having 3 windings. Now the conductor may be considered as a coil. If the EMF is induced in a coil and coil is a closed path, then you can say that the current will flow through the coil. So this is my AA dash, which will form the complete coil. You can say that this is my conductor 1 or conductor named A. This is my conductor named B, and this is my conductor named C. In earlier case, we were discussing the power generation for the single phase. Now as in three-phase system, it is three-phase. So all these coils are mounted on a stationary part, say, which is 120 degree apart. That means A and B are 120 degree apart, and B and C are also 120 degree apart, and A and C are also 240 degree, minus 240 degree, or you can say that the plus 120 degree apart. Now in this case, in previous case, we were considering that the magnetic field was stationary and conductor was moving. In this case, we are saying that the conductors are stationary, because now this is three-phase system and conductors are mounted on this yoke, or say the stationary part. Right now yoke is not known word for you. You don't know what is yoke, but it is a stationary part of the generator. Okay, so here the conductors are mounted on a stationary part, and you are having say the permanent magnet which is moving or say rotating. So again, the three essential conditions should be: there must be the magnetic flux. So magnetic flux will be there due to this permanent magnet. This is the north pole of the magnet, and this is the south pole of the magnet. There should be conductor. That was the second essential condition. Here we are having the conductors. We are having the three conductors. In each phase we are having one conductor. So in three phase we are having three conductors. And third one, that is the relative motion should be there. If this rotor, if this part is moving, we are saying that it is rotating. So we are saying that it is rotor. This part is not moving, so it is stationary. So we are saying that it is a stator. Okay. So now if this rotor is moving or rotating at some constant angular velocity, then the magnetic path established by it will cut the conductors, and EMF will be induced in it according to Faraday's law. So if this is the case, then now you can say that we are having the three windings A dash, BB dash, CC dash, all are 120 degree apart. Okay, and the rotating part, that is the magnet, that is the permanent magnet, and N and S pole is there. Okay, so now in this case we are having the rotor. We can say that the three-phase EMF will be induced, and this three-phase EMF induced is as shown in the slide. So now here you can say that the system can be considered similar to this system as we described previously, and it will induce the three-phase EMF like this. This is your phase 1, phase 2 and phase 3. So now here you can say that both the system are same. In previous system, the rotor was rotating and the conductor are stationary. In this system, the conductors are rotating and the magnet is stationary. Both are the same system, because in both the system anyhow we are getting the relative motion. So if this is the kind of a circuit, then we are getting the output voltage like this. As the three windings or three conductors are placed 120 degree apart, you can see that this is your phase 1. Okay, it starts from 0. So your phase 2 starts from 120 degree. So phase 2 lags by phase 1 by 120 degree. Phase 3 starts from 120 degree after phase 2. That is after 240 degree of the phase 1. So you can say that the phase 3 lags by phase 1 by 240 degree. The same thing can be told like that. Phase 2 leads phase 3 by 120 degree, and phase 1 leads phase 3 by 240 degree. So that is the thing that we have discussed right now, and here is the final. You can say that if we are having this kind of configuration, the output voltage generated will be like this. And here we are saying that it is phase 1, 2 and 3 are at different instant of time, and relative to other phases, one phase must be negative at least, two phase will be positive, one negative or two negative or one positive. So here we have discussed the generation of the three-phase EMF. Okay, that is the generation of the three-phase voltage. Generation of single-phase voltage or three-phase voltage both follows the principle of Faraday's law of electromagnetic induction. Only the thing is that in case of three-phase, we require three conductors or three windings. Winding, that we are saying that winding consists several conductors, but all are having the same phase is known as one winding. So in case of the three-phase, we are having three windings, A, B and C. A winding and B winding will have phase shift of the 120 degree. A winding and C winding will have the phase shift of the 240 degree, and hence the EMF induced will be the three-phase sinusoidal voltage as already discussed. So this is the basic concept how the three-phase EMF is induced in the generator. Once it is induced in the generator, then it will be transmitted, distributed by three phase, and then in our successive lecture we shall discuss the three-phase terminologies. Thank you.